All right, so we are going to go over evaluating limits in this recording, and we are going to focus on taking the limit of functions that might have a jump discontinuity. We spent a little bit of time recently going over limits of functions that had removable discontinuities, which were holes in our graphs, and they presented themselves for those examples in the form of rational functions where we had a common factor in the numerator and denominator. Anything over itself is 1, we could remove it, but being that there was a variable x involved in the expression or the factor, the common factor in the numerator and denominator, that caused for a discontinuity to exist because some value of x will make the denominator 0, and that value needs to be removed from the problem. So we worked on that. We talked a little bit about limits at asymptotes. We talked about approaching from both sides. So we even introduced for like a minute one-sided limits. So in this case, that's what we have here. A one-sided limit, x is approaching, in this case, -1. So on this graph here, -1, kidding, that's +1. -1 is that x value right over here, right? We have 1, 2, 3, 4, -1, -2, -3, -4. So -1, okay, right there. If I'm worried about approaching x, approaching that value of -1, how do we approach that? We approach it by basically closing in from both sides. So kind of think of like a Indiana Jones trapped somewhere and the walls are closing in, yada, 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 right? So if you're closing in at -1 from the left is referring to this side here. From the right is referring to this. This little plus sign in the exponent means from the right. So that's definitely something, write that down, because sometimes people think it means going towards the right. It is from the right side. So we're coming from the right to -1. If we were not, if we didn't have anything here, it was just approaching -1, since we have a very, I hope, clearly obvious jump discontinuity right here, a jump, that's where you clearly pick up your pencil, jump to a new y value, even if it's very close. If it's a different y value, you're still jumping. So you jump to a new y value to carry on, that's a jump discontinuity, and that would definitely mean your limit is not meeting up from the left and the right. If there was no plus sign, the limit would be DNE, does not exist. Okay, we usually write a capital D, capital N, capital E, done. But here we're just asking about the right side. Okay, so coming from the right. And the limit is only asking you, well, if we're coming from the right side, what is the y value or the output? What is the function approaching? So you don't have to get there, as indicated even by this big open circle right over here. We don't have to actually reach the point. That's not what it's about. It's just about what does it look like you're getting closer and closer and closer to for a y value. Will you maybe get there? Sure, maybe, and maybe not. So what y value does it look like we're approaching for this one from the right side? So we're coming this way, this way, this way. The y value we're approaching is?
Four.
Yeah. Bam. Okay. So it's 4. Now, is there a way to do this one without the graph? Yes. We can learn about this new, I like to call it a parent function. It's really the quotient of two parent functions, where one of the functions is just y equals x, a linear, and the other one is y equals the absolute value of x, and we are dividing those, and then from there, okay, we have some shifting and stretching going on, but we're going to save that conversation for a different day. So let's look at the second example. All right, in this example, we are approaching -1 again, but instead of approaching -1 from the right, and it might be a little hard to see on this view, it does say instead find the limit as x approaches -1, and then up here we have a little negative, so from the left of, find the limit of what? Of f of x, I don't know why I wrote it like like that, of f of x. And then it says comma. So that's like it's saying, oh, find the limit of, as x approaches -1 from the left of some function f of x. The function f of x is, and we write it on the side. Whenever it's a piecewise function, like this one's about to be, we don't really write it right next to it because you would end up writing this big curly bracket, and then it's just going to be kind of weird, okay? So we're going to have our equations over here, right? So the name of this type of a function, when it's written in this way, is a piecewise function because it's pieces of a bunch of functions, and when you put all those pieces together, it's still a function because it passes the vertical line test. We also saw this curly bracket when we did systems of equations, but that's different. So systems of equations maybe looked more like y equals 2x minus 5, and then like, I don't know, 3x minus 7y equals 8, whatever, something like that. In this case, like you have two full equations and they're all to the right of the curly bracket. This is just saying they're on the same graph, whereas here, the y equals, or the f of x equals, is out on the left. So they're sharing what y equals, and we're given other details to the side here. So this one here, I think you could read it. It says we have on top a linear function with a slope of -1, if you think mx plus b, -x minus 8. And we only have that function when x is less than or equal to -1. So really, that's the left side of -1, a linear function. So again, -1, just going to pick a color here. So -1, I might refer to that on occasion as like our boundary or our boundary number. So it's like the number that's separating as a boundary between one function piece and another function piece. So there's that -1. And -x minus 8, that's the output value. Those are the y values that we're looking at. They're generated depending on the x values that we plug in. But which x's are we plugging in? Only x is less than or equal to -1. So we will not have any of that over here, okay? If it did, we would erase it, but not the most efficient way to graph by graphing everything and then erasing. That's like kind of crazy times. So this over here is what is responsible for that graph right there. Now, they gave us the graph, and that's nice of them. An easy way to do it, if you ask me, is plug in the back. This is important. So, you know, if you pause it and rewind it, or pause it to write it down, but you should definitely plug in the boundary points as an x value to get the y values on the boundary, right? When it's something like this, -x minus, so it's really y equals that, -x minus 8, and I could say x is less than or equal to -1, or we could write it with interval notation, which looks like -∞, comma, -1, and a bracket. When we fill in the boundary, okay, for x right over there, we will do that even here when it's greater than -1 without the equal sign. Instead of drawing a closed circle at that point, we'll draw an open circle at that point. It's still an open point, and it's still a point. It's just not where the function happens to be actually defined. It's open. It's just marking a spot like a placeholder, you know? So, when we have y equals, another thing I don't really love about y is when you do the work, negative, parentheses, -1, close, minus 8, which is going to be y equals +1 minus 8, right? And that's y equals -7. I don't love how the answer looks at the end because it looks like your answer is an equation. Anytime you have y equals, that's a horizontal line at that y value. This we're supposed to use in conjunction with the x value and generate a coordinate point for us. I'm going to draw it colored in square because everywhere I have a closed point, I'm going to draw a closed square to remember that it goes with the square bracket. And that will be at the point, ordered pair, x comma y, which is, in this case, -1 comma -7. All right? So -1, -7, go left 1 and down 7. That's this point right here. Okay? That's a good point to know. Don't start at the y-intercept. That is the baby way to do it. we're big kids now. Don't plug in this case, -8 and go from there. Next, the slope, negative out front, is -1. If I were going to the right, down, over, down, over, down, over, blah, blah, blah. So be careful when you go to the left instead, because we're going that way. Be careful when you go to the left, because people will accidentally be like, oh, -1, down 1, left 1, down 1, left 1. But if you do that, down and left, like your line is going to look like this. And remember, we read from left to right. That's actually a line with a positive slope. No bueno. So remember, if it's got a negative slope, when we go left, we go up. When we go right, we go down to make a negative slope. And that's how I would graph the line, okay? A little cheat way, a little method. Now, the boundary point for this, so I told you I don't like the notation with y. Let's talk about why I like f of x better. So if you were looking at f of x equals -x squared minus 4x minus 4, if I am filling in the boundary, -1, f of -1 equals -1 squared minus 4 times -1 minus 4. I'm squeezing it. I think you could see it though. And then just be careful with PEMDAS, the order of operations over here, okay? F of -1 equals exponents first, -1 squared is +1, and then times this negative, because that's really times -1 out front, okay, is -1. -1, negative, that becomes +4, minus 4, adios, those are gone. And you're left with this, and I like this better because it tells a full story. F of x is y. F of x is y. So the x is -1, and that is what causes the y to be -1 as well. And because it is greater than, that'll be an open point. So it's an open point, right? X comma y equals -1 comma -1, and that's why that's right over there. And really, do I care about the right side of this graph? To be honest, no, not for a limit. We really don't care right now what the right side of this looks like at the moment. I know it's continuous because it's a polynomial, it's a quadratic, that's great, but it doesn't matter. It doesn't matter where the rest of the graph goes if it's continuous and you know where it is at the boundary, because where are they going to ask about the limit at? At the boundary. They always do. Once in a while they might like throw you a curveball, but really that's always what's going on. So we're approaching -1, the boundary, from the left, so along the yellow graph. If you look at the picture, we could tell what the answer is. If you look at the picture, I hope that we could see. I'm just going to rewrite it as a full thought. Always a good thing to do. The limit as x approaches -1 from the left of f of x, and f of x is defined above, is... Do you want to say the answer? You want me to do it? Ooh.
You can say it.
Thanks. Is -7. Okay? Because we're approaching from the left. That's the y value. So that would be the limit. That's the answer right there. Now, do you need a graph? Again, you do not need the graph to do this. You can do it without. How do you do it without? You're approaching -1 from the left. Decide which side of this shows you the left. Well, the left will be less than or equal to -1. Do direct sub right there. Boom, you're done. As long as it's nice and continuous beforehand. All right? So that is the end of example number 2. Now let's just talk about another thing for just a minute here. What if instead, I'm trying to like hold this really close, and I had it, okay, and I messed it up again. What if instead of this approaching -1 from the left, what if it was just, let's approach -1? So that means we got to approach from the left, we got to approach from the right, both sides, and we need to know what are we approaching. I'm going to tell you right now, this limit does not exist, okay? Because you are approaching -7 from the left, and from the right, the y value you're closing in on is the y value of -1. But how the heckers do you get that from up here, right? Well, you check the left and the right. So from the left is this top equation. Fill -1 in there. From the right is the bottom equation. Fill -1 in there. If there are different numbers, capital D, capital N, capital E, does not exist because the two y values don't match. If they are the same number, that just means that this open circle and this closed circle, like these graphs are slid, whoop, together and make a continuous graph. And we see that in a couple of these other examples. I could kind of show you one in just a second, but that's how you would do it and figure it out. So we kind of did do that work a little bit over here. I could kind of indicate a smidge with the highlighter. So the yellow, we plugged in -1 over here. That's where we got that. Sorry, it's dark when I'm kind of pulled back over here, but there we go. That's the yellow side of it. And then the blue is really, here's the work over here. So here's an open circle because it was greater than, and we plugged in that boundary number again. And so we got a -1 here. That's technically the right hand limit. We could call it the right hand limit. Over here, we got -7. That is the left hand limit. And limit's a better word to use anyway, because we can't say the graph is at -7, when x is -1 over here, but when x is -1 over here. Wait a minute. We can't really say that because x is never -1 for the blue one. It's only greater than -1. So that's why we say limit, because the limit you don't have to get to the point. So it's a better way to describe it. So we got -7, -1. They are not equal. So you would put D and E does not exist. If they were equal, what would that look like? Well, that would look like, I won't do this example right now, but I would always say when they give you the picture, take advantage and do the limit graphically, but also cover up the picture and say to yourself, how would I do this without the graph? In other words, how would I do this algebraically? Okay, so this is what happens when the left and right hand limits equal one another. I promise if you fill -3 in the top and you fill -3 in the bottom for your y equals, because it equals both of those at different periods of time, your y value is going to be equal. What is it going to be? Well, if I had to guess, it's going to be, sorry, it's so bright, -3. That's where they meet up. So do we see the open and closed points? No, because they just drew it, and where one graph ended, the other one started, and you continue. So I always describe piecewise functions as like that relay race where you pass the baton to the next runner, and if you drop the baton, no good, right? I think you basically lose the race or something. I don't know. I wasn't a runner in high school. I don't know. But I know there's a baton thing. That's a thing. So if you drop the baton, that looks like this. Like one graph ended, the other one started. They didn't line up. Like womp womp. And then if you pass the baton successfully, well, then they lined up perfectly, right? You sent one thing out, and where it ended, the other one started and picked up exactly from there, okay? And just to show one more, I prepped one, I thought. Yeah, number 12. So I'll just give this a couple minute go at it. So here's an example of one, just like what we were just talking about, where, oh boy, too bright, wrong way. We don't have a graph, right? We have instead just the piecewise function, and it's asking us, just to rewrite it a little bit bigger, to find the limit of f of x. I'll pronounce this one, speak it differently. The limit of f of x when x approaches -2. No plus sign in the exponent, no minus sign in the exponent, so it's not a one-sided limit or a left-hand limit or a right-hand limit. It is just a general limit. So in order for this limit to exist and have an answer, that really means that the limit as x approaches -2 from the left of f of x equals the limit as x approaches -2 from the right of f of x. If they're equal, the limit exists, right? They match up, that's what it is. If they're equal, it exists. But if they are not equal, then the limit as x approaches -2 in general of f of x, d and e, does not exist. So if the left and right hand limits don't exist, if they don't equal one another, that's what we'll talk about right now, then the general limit, does not exist because they don't meet up. That's all it really comes down to. So fastest way to do it without graphing, plug it in the top, plug it in the bottom. Check both the left and the right. So the left, we're going to approach -2 from the left. Which one's the left? When x is less than or equal to it. So how do I do that? Well, that equals, direct sub we're going to do, negative 2 squared, which equals 4. So the left-hand limit is 4. Now, this one, normally I would write equals next to it, but equals, I'm going to take now, as we approach negative 2 from the right, x is greater than or equal to negative 2, that's the right. So let's direct sub in there. So negative 2 is going in my numerator, but I had a negative out front. I'm just going to make those longer so they don't look like a negative. That's a negative, and that's a negative, sorry. Over 2 plus 3. 2 negatives, obviously positive. 2 over 2 is 1, and 1 plus 3 is 4. Ooh, 4 equals 4. Well then, therefore, no pun intended, 4 equals 4, therefore, the limit as x approaches negative 2 of f of x is, you always have to write something after limit. You can't just leave it blank and be like limit equal sign. Like, it's like leaving it an empty square root or a fraction with nothing in the numerator. Like, put 1 or x or something. Equals 4. Winner, winner, chicken dinner. So a little bit breakdown. So this side over here, indicated on the side with the blue arrow, got that answer. That came from this piece. Okay, and that was the limit as x approached from the left. And then over here, this one over here was referring to this over there. And where did we do the work? We did the work right there, and we got that answer. They were equal. So our final answer was 4. And that is really what it comes down to. It just takes a lot of discipline and practice and making yourself like remember the rules and not just like be like, yeah, I get it. No, like really force yourself to do it a bunch of times, do a bunch of practice problems, and keep revisiting what you did in another example until you remember how to do it. Because conceptually it's easy when someone who knows what they're doing is explaining it to you. But I remember when I first learned limits, whew, like I was like, yeah, I get it in class, but homework, tests, I was like, I have no idea. Like, I was so confused. So hang in there and keep practicing and trying as best as you can on them.